Quantum computing is the future of human technology, but it has a massive burning problem. Heat. At the quantum level, even a tiny bit of heat destroys information instantly. To fix it, scientists did something absolutely insane. They took the enemy. They used noise, the very thing that breaks quantum states, to actually cool the system. This is the world's first noise-powered refrigerator, operating at the scale of single atoms. A breakthrough that finally opens the door to a new era of computing power. Let's dive into the details for the topic.
All right, let's dive into something pretty wild today. We're talking about a mind-bending breakthrough in the world of quantum computing, where scientists have taken one of the biggest problems standing in the way of powerful quantum machines, unwanted noise, and somehow turned it into the very solution they needed. Yeah, I know, it sounds totally paradoxical, right? But in the super strange world of quantum mechanics, that is exactly what a team of researchers has managed to do. They looked at this fundamental obstacle and decided instead of fighting it, they were going to harness it. Okay, so to really get your head around just how clever this whole thing is, we first need to understand the central conflict at the heart of building quantum computers. It's a classic catch-22 that has had engineers scratching their heads for years. Let's break this down. On the one hand, you absolutely positively need things to be incredibly cold for these quantum states to even form. But here's the kicker. The very systems you use to create that cold inevitably produce vibrations and electromagnetic interference. In other words, noise. And that noise is like poison to the delicate quantum information you're trying so hard to protect. So why all the fuss about the cold? Why is it so non-negotiable? I mean, why go to these absolutely insane lengths to create these frigid environments in the first place? Well, we're talking so cold. We're talking temperatures just tiny fractions of a degree above absolute zero. That's colder than the vacuum of deep space. And it's at that point, and only at that point, that certain materials become superconducting. That means electricity can flow with zero resistance, which is just essential for these quantum circuits to work at all. And at the very heart of this whole problem are the qubits. These are the fundamental building blocks of a quantum computer, right? And the thing is, their quantum states are just unbelievably fragile. I mean, the slightest bit of heat, a stray electromagnetic wave, and poof, it can knock them out of their state, erasing your entire calculation in an instant. And you know what? This problem just gets exponentially worse as you try to build bigger, more useful quantum computers. More qubits means more components, which generate more heat and create even more pathways for that noise to creep in. It's been a massive roadblock to scaling up the technology. But this is where the story takes a really fascinating turn. Researchers over at Chalmers University of Technology in Sweden decided to just stop fighting the noise. Instead, they asked a brilliant question. What if we could actually control it and make it work for us? Now, to be fair, this idea of turning random fluctuations into a tool for cooling isn't totally out of the blue. It's actually a concept that physicists have been kicking around for a long time, even if nobody had ever really managed to make it work in practice. It even has a pretty cool name, Brownian refrigeration. The basic idea is that the random jiggling of particles, which we usually just think of as heat, could actually be directed to create a cooling effect. It was this beautiful theory, but for a long time, just a theory. Well, until now, this work from the Chalmers team is the closest anyone has ever come to making that theoretical idea a reality. They didn't just write about it, they actually built a device that does it. Okay, so the crucial question is, how on earth did they pull it off? Let's get into the really ingenious mechanics of this tiny quantum refrigerator. At the heart of it all is something they call an artificial molecule. Now, it's not a real molecule like you'd find in nature, but a complex, custom-built superconducting circuit that's designed to behave like one. This little component is the key, and it sits right between two microwave channels. The process itself is surprisingly elegant. First, you have a hot side and a cold side, and the artificial molecule acts like a little gate between them. Then, and this is the genius part, they inject precisely controlled microwave noise. This noise doesn't just add chaos, it acts like a tiny traffic cop, actively steering heat away from the cold channel and pushing it into the hot one. And the level of control they achieved here is just mind-boggling. They can measure and manipulate heat currents on the scale of attawatts. An attawatt. That's a decimal point followed by 17 zeros and then a 1. It's an almost impossibly small amount of energy to even think about. I know that number is hard to wrap your head around, so to put it into perspective, one of the lead authors gave this incredible analogy. A heat flow this tiny would take the entire age of the universe just to raise the temperature of a single drop of water by 1 degree Celsius. The age of the universe! That's the kind of precision we're talking about here. So look, this is way more than just a cool science experiment. A breakthrough like this has massive implications for the entire field of quantum technology. It really helps build a path to the future. And what's really amazing is just how versatile this little device is. By tweaking the noise and the temperatures, it can be a refrigerator, pulling heat away from a very specific spot. But it can also be a heat engine, using a temperature difference to do work, or even a thermal amplifier. It's basically a Swiss Army knife for quantum thermal management. And here's why that matters so much. Conventional cooling systems are like these giant freezers. They cool the whole environment. This new device, though, allows for surgical precision. You can manage heat right where it's generated, inside the quantum circuit itself. That is a total game changer for building stable, large-scale systems. As one of the researchers, Amir Ali, puts it, this level of control is what will ultimately lead to more robust and reliable quantum computers, the kind that can actually solve real-world problems. They've turned the enemy, noise, into an ally. So it leaves us with this one final, powerful thought. For decades, the focus has been on building bigger and better qubits. But maybe, just maybe, the real key to unlocking the quantum age wasn't about the qubits at all, but about finally mastering the subtle, chaotic dance of heat and noise.